talking about what are chain reaction machines, and specifically Rube Goldberg machines, which are a type of chain reaction machine. We'll introduce Rube Goldberg's and cartoons of chain reaction machines, and give an example of real life. And I don't know why we might be talking about it and having you at a table with a mystery box with that. So chain reaction machine, it's a machine consisting of a sequence of steps where each step is the result of one preceding and the cause of one following. And here's an example of a type of chain reaction machine where you're looking to accomplish a very simple task in a very complicated manner. We all know people like that. So this is Rube Lucius Goldberg, engineer for 6 months designing skewers, and left engineering to become a cartoonist. So we don't actually, as engineers, do Rube Goldbergs very often, but there's a lot of engineering involved. And Pulitzer Prize-winning cartoonist, sculptor, and author drew machines that completed simple tasks in extremely complex and roundabout ways. The ultimate STEAM experience. But he actually never did anything. Oh, he just cartooned them. All right, so here's a simplified pencil sharpener. So the window opens, A, causing B, the kite to fly, which C, pulls the string, which D, lifts the cage door, which E, the moth escapes, and F and E, flannel shirt, causing G, the shoe. And the electric iron then heats up, burns a hole in the garment, smoke forms, K enters tree, forcing a possum out and into the basket. The rope moves and lifts the cover of the cage, allowing the woodpecker to chew on the wood and then sharpen the pencil.
But then we have safety precautions.
Knife always handy in case of the opossum. Somebody gets sick, it can't work. So here's an example video of an actual Rube Goldberg machine. All right. So anybody who's ever watched Tom and Jerry or Scooby, or I wrote Odesma on Sunday because my kids were watching Lego Beleaguered, and it was when Batmite had his own Rube Goldberg machine. And so it's a frequent occurrence in complicated cartoons. I think the music really adds to the Rube Goldberg. I suspect we won't have music. Looks like we're going to get something else. So I wonder what this machine is going to do. I don't believe we supplied you with fire. I don't think there's any mice hiding in the box.
I would have taken that.
Wait for the next page.
So what simple task, here's the quiz part of, what simple task did the chain reaction machine accomplish? And so the overall point of the Rube Goldberg, or at least the simple task that is accomplished after many tasks, is always the final step in the Rube Goldberg. So I'm passing off to Aaron. Aaron,
Okay, so the essential steps that we're actually going to have you guys implement have a certain vocabulary to them. And so the smallest action that will be performed, and using the previous example that we showed on the PowerPoint, is called a step. So each thing that was happening, and when Kathleen showed A, B, C, or D, they were open a window and fly a kite, pull the string that will then open the door, and each of those are small individual steps. And it's the smallest you can possibly go in terms of making this whole machine. And then the compilation of all of those steps is called a module. So a module has to have at least 2 steps within it to be considered a module. And so when you collectively group those steps, depending on what sections of each machine you want to put, as long as they have at least 2 steps, you consider it a module. So for example, in this example, it was for 8 steps A through F, from opening the window to having the moth eat the flannel shirt. And then when you put it all together, it's just called a machine. So depending on how you group the steps and you group the modules, you can have anywhere from at least 2, but anywhere beyond that, modules in each machine. So as long as it's grouped in order to get from the first step to the last step, which is ending up sharpening the pencil, you can group them as long as it's based on at least 2 steps within modules that have at least 2 modules in one machine.
Okay, so we are going to have a lot of fun, but we are science teachers, and this is an NGSS workshop, so we do want to make sure that we're thinking throughout this about the connections to NGSS. So maybe before I go to the next slide, come back for a second, anything you already saw in just the description? Because you all are NGSS sensitive, right? So I heard some things over on this table.
What was the question? We were talking about chemistry, to give you a transfer of energy.
There's a whole bunch of energy things. The students are going to choose, and you're going to choose what kinds of steps you have. But some of those steps could talk about different forms of energy and translate between different forms of energy, right? So chemical energy, electrical energy, kinetic energy, potential energy, all of those are things that could be put in here.
How would you make this relevant towards biology?
Biology is the harder thing, so we're going to ask you to step back. Well, there was a mouse in there, but that's going to be the harder thing. So those of you who teach biology, we want you to think not as much about how you're going to get that content piece in, but about how you might do a lesson along the lines of what we're thinking. And we're going to debrief that at the very end. I'm hoping maybe if you think about it now, it might help you. So there's some pieces of, subsystems and things like that maybe you can find some ways. Were there a couple more examples of?
Cross-cutting concepts. You can use lots of different principles from different areas to achieve your machine.
Right, so some of those cross-cutting concepts might come into it. Cause and effect is, so if we go to the next slide, that's all over this, right? Because you're gonna do something and then you're gonna see what the impact of that is. Some of these, the energy ones, I think, are the ones that come up first, especially for chemistry or physical science teachers. Gravity can come into play in some of these things. You'll see motion and stability. You could, for example, have students actually analyze some more of that if you're in a physics class. Hypothesis testing, what's going to happen when I do X. It's also real good on the cross-cutting concept of systems. You're going to use the vocabulary that Maren was just talking about, and you'll be designing not only the steps, but then the modules, and then your super team is going to make one overall machine. So this is a nice way of being able to see the little pieces. And then Odesma's going to talk to you about how we can mathematically look at, say, the reliability of each of those pieces or subsystems or modules and how that impacts the overall. So it's a nice one for that too. Oh, and it's also, it's fun, so hopefully people aren't like they felt when you took the test this morning. It's a way to get people engaged with each other as well as with the stuff. We said it could also apply to the science and engineering practice where students are planning and carrying out investigations and trying their own sort of new things. And so as they're using materials, when you do get to open the super secret box, you'll find that some of the things in there are very familiar to you, but they may not be things you're used to seeing in your classroom. And so using the imagination and figuring out new ways to use things is an important step here too. So there'll be a whole bunch of common objects that'll be used in a new way here. By the end of today, we will have 6 very different machines. I guarantee they will not be identical, and that is one of the good things, particularly from the engineering standpoint. There's not one right answer to this question of how do you turn a page or pop a balloon or whatever. And so you get to see creativity, you get to see a variety of solutions. You can talk about what makes one better or worse, or what makes them different, how did they get to those. And this ties in with the science and engineering practices, as well as the first content standard within the engineering and technology standards there, which has to do with designing. And although it doesn't specifically say in any of the standards anything about teamwork or collaboration is critical to doing engineering design wherever it's done. It's also really important pedagogically in how to implement some of these things. It is doing a Rube Goldberg machine by yourself, I think, would be a pretty daunting and not that fun experience. The fact you're going to work together is going to make it a lot better. Most of the active learning pedagogies that we're hoping you're employing as you do NGSS really do require students to work in teams. You also may not have the resources to be able to do it if you don't have people work in teams. And so, although it doesn't say anywhere that engineering has to be teamwork, certainly engineering must be teamwork from my perspective, and I don't see how you can do most of the NGSS pedagogically without doing teamwork. So this is a nice example of the collaboration, and the collaboration that sort of needs each other, because as you're making individual modules, you have to interact with the other modules to make the overall machine successful. So now Odesma's going to give you an overview of what you're actually going to be doing.
Okay, so the challenge. In the allotted time, and it's about 2 hours, each cluster, so we have 6 clusters, will design and build a chain reaction machine with a minimum of 10 steps, and the goal of your machine is to pop a balloon in an elaborate way using the materials provided in the kit. So you have these big kits, and we will soon reveal what's in those very big kits. All right, so I want to bring us back again to the engineering design process. And the goal here is that we want to begin to develop this disciplined approach to tackling a problem. And so I know immediately our biology teachers are saying, well, I'm not seeing the biology in it. But for now, trust us that what we're really trying to emphasize here is a means for us to develop this disciplined approach to solving a problem. So, now, one of the tools that you may want to give your students, and we are encouraging that you consider using this, is a template that sort of maps out how that engineering design process can be used in a particular task. So in this case, we're thinking about developing or designing this machine, and so we first start off needing to understand what the goal of our machine is or our system. And the first part here is asking the questions about what are the requirements. So one requirement that we are giving you is that it must have a minimum of 10 steps, and then we're going to collectively decide on what the additional requirements need to be for this machine. After you sort of identify those steps, you want to start thinking about possible ideas that you can use to incorporate in your machine. Then you might move on to a planning of it, where you might select which steps actually fit your requirement. You might want to sketch what the modules may look like. We're going to talk about creating this cluster diagram, which I'll move on to shortly. No, that's fine right here. And then we create, we test, and then we improve. Alright, so this here is a type of block diagram. So block diagrams are used often in engineering to help us understand how various subsystems interface with each other to create a big system. And so here, going back to that vocabulary Maren shared, we're looking at modules and how modules relate together to form this big machine. So the key thing with a block diagram, we want to talk about what are the inputs and outputs to each of your subsystems and how those inputs and outputs connect so that we have all of these modules working together to form our machine. So in this example here, I don't know if you can see the illustration of that chain reaction machine, where the goal here is to make toast. And so we can divide this into various modules, where our first module, the input of it here, is where we turn on a fan to propel a pin. And the output of that particular module here might be where the balloon pops and releases a weight. If that last step of that module is this releasing of the weight, then to connect to the next module, we have to have that released weight activating a lever. Then the end of that step there, or that module, might be pushing a pedal to close the scissors. And as you can begin to see how, if we just look at the output of one module and the input of the one that precedes it, you begin to see the relationships must exist between those two things. So one of the things we want to encourage, first of all, is that's why we initially broke you up into teams of 3. So we would like each team of 3 on your big sort of super team, as Kathleen called it, to probably think about designing a module. And then you begin to put the modules from each of your smaller teams together in your big super team to create that machine. And so it's going to be really important that each module begins to think about what's the input that's coming into my module and what's the output that I'm sending to the next module. And so we're asking that you begin to document that in this form. So we're going to give you some blank sheets. So each big super team gets this sheet, and we really want you to, as you first start to work in your smaller teams, think at the end about what's your input and what's your output and how that's going to connect to the next module so they can then create their set of steps. Now, if you are familiar with Rube Goldberg, how many of you have done Rube Goldberg before? Okay, so a few of you. Often with Rube Goldberg machines, if you see them, at least when they're done for competitions, for instance, they tend to have a theme or story behind it. It makes it kind of interesting. And sometimes that story and theme also helps in that creativity about thinking about these elaborate and interesting ways that you can in fact accomplish this task. So this is optional, but I'm encouraging it. You might want to just think about giving a theme to this machine and then trying to come up and tell a story by the different actions that you will actually implement in this machine. So in this example here, we can have a theme about celebration. And maybe the story is for Independence Day, we go to the amusement park, ride the roller coasters, go on the water slides, and in the evening we drive to the park and we see the fireworks. And so we can have where a simple thing where the ball rolling down the ramp, that symbolizes being on a roller coaster. The dominoes moving shows sort of the water aspect of a wave, so maybe that's like the water park part. And then as this lever movement causes this car, so that symbolizes us moving towards the park, and then the popping of the balloon here is sort of that fireworks. It could just make that story a lot more interesting to the viewer if there's something besides just looking at these cool mechanisms, but we're actually seeing a story taking place. Now, as Susan mentioned, one thing we always want to say that as we go through this very disciplined process, we're gathering data to help us as we begin to improve on it. And so in a chain reaction where we have a very sequential system, we begin to understand that one fault in the system actually affects the total outcome of the entire machine. And so one mechanism that we want to sort of introduce here for how you can become more systematic about thinking about where do you want to begin to make improvements is looking at calculating the reliability of your machine. And so this is also a good example of how you begin to introduce mathematical types of computations in a lesson that also has that engineering piece to it. I mean, as we said, engineering is based on the natural sciences and the mathematics, so it has to also be there as well. So when we calculate the reliability here, again, we're doing it where we start with the smaller subsystems, so the modules. And what we try to say is that you want to first measure the reliability of every single step in that module. And so as you find the reliability of every single step, then the reliability of the overall module becomes the product of each of those individual probabilities or reliabilities. So for this example where your module is ball rolls down ramp, dominoes fall, all the way to car rolls away, you can imagine if you did 10 tests on each of those steps and you came up with the individual reliabilities, and then as we found the product of all of those, we come up with sort of a measure of what the reliability is of that overall module. Now, of course, as you look at this, you say, oh my gosh, it's 23% reliable, that's not really good. But what it does begin to help you realize, well, one, of course, your machine is going to be less reliable than your least reliable step. That's a good sort of takeaway for some of your students. But then it gives them a point to say, well, now I know where I need to start working on. I need to probably improve on the step where the dominoes are falling down, because that's probably one of the areas where I have the least level of reliability. So here's the data that now can drive how you begin to improve and revise your design. And then once you have that data for each of your modules, you do the same process in coming up with what the reliability may be for the overall machine. And so again, you just find the product of all of those individual module reliabilities to come up with what the reliability is of your machine. Of course.
When you're talking about the reliability of each step, if you have a failure of an early step,
Mm-hmm.
how can it impact the later steps? Or you test, when you do your trials, you testing each step as individually?
Correct. Yes. So one of the things we'd like for you to do in your big teams is to document what your reliability measurements are for each of your modules and how overall what you think the reliability might be for your machine. I think you probably are going to have 3, yes, because I think we have three to 4, depending on how many modules you have.
I didn't hear it yesterday.
Yeah.
They're learning about their machines before machines are here.
All right. So as we begin this disciplined approach to attempting to tackling this problem, what I would like us to do together is start that first ask step where we define the problem together. So the first part of it, so I'm saying is, we know the goal is to pop the balloon. So that's the first thing. But beyond just understanding the goal, we need to know what are some of the requirements or constraints for this problem. So the first requirement we're giving is that it must have a minimum of 10 steps. You can have more than that, but collectively you have to have 10 steps. What we would like is that each super team identifies one requirement that we will all then adhere to when we design our chain reaction machine. But to get you started, I'm going to have you take some time, so about 5 minutes first, to get acquainted with who's on your super team, and then get acquainted with the materials that are available for you to do this task. Then we will reconvene, and then we will each begin to think about what are the additional requirements that each team will contribute. So some examples might be, you must use a kinetic energy source if you want to bring in some energy aspect to it. Or it must be, you must use a particular object in it. Or you might say you must have 5 different types of simple machine, or 2 different types of simple machine.
Today I can do that for you, but
So go ahead and explore the box, explore who's on your super team, and then we'll reconvene. Teams, can I get, let's just get your attention before you go off again. So we have one requirement already given from, so we can call this team 2, if I'm just going in order, team 2. Super team 2, and must have an airborne step element. So everyone has to have at least one airborne step element. Okay. Team 1, are you ready to give us one? Must start 3 feet high.
3 feet above the table.
But that's the start. Okay.
The first 3 is module 1, right?
So is it one component, or the start must be 3 feet high? So you must have a step that's 3 feet high. Is it from the ground or from the table? From the table.